Okay, the next section, 7.4, is not much different. What we did is use the metric system to convert between different multiples of the one unit. The length unit in the metric system is meter. And we looked at decameters, we looked at kilometers, we looked at centimeters and so forth, and converted between them simply by shifting the decimal point and the number that we have, either to the right or to the left, using the prefix line. And let's put the prefix line up here. I'm sure we've all memorized the little technique for doing the prefix line because it has food in it. Yeah, here's your basic unit. Yesterday was the meter. Okay, then you have one here, and one here. This is K for kids. Have donuts until U for unit. Dad calls mom, right? Everyone got it memorized? Very much like PEMDAS, right? Okay. So this is a kilometer. This is a hectometer. This is the decameter, which is simply 10 meters. 10 meters. This is the 100 meters. This is the decimeter. This is the centimeter. And this is the millimeter. Okay, so we use that to go between different sizes of length. If you're going to San Francisco, you're going to talk about kilometers. If you're maybe going across the campus, you do a hectometer, and so forth. When you're talking about the width of this, you'd certainly talk about centimeters, huh? Something like that. Okay, now what we're going to do is go to the other types of measurements in the metric system. We always have things like mass and capacity, and they do have these things in the metric system. Mass corresponds to our weight. We talked about it yesterday. Mass is the same throughout the entire universe. Weight changes from point to point. Okay? It depends on the pull of a certain body, like a planet or a moon. And mass does not depend on the pull. Anyone had any chemistry? No? In high school? No. There's something called Avogadro's number. And it has to do with the number of atoms inside a certain space. Okay? Well, yes, that number is constant for all substances, but those atoms are larger or smaller depending on what you're talking about. If you're talking about iron, the atoms are heavier. If you're talking about something like helium, the atoms are very small. All right, so it's that mass that stays the same. It's the number of atoms that stays the same. If you took this thing up to the moon, the number of atoms wouldn't change. Okay? So it has some quality that doesn't change as you move it around the universe. Sometimes it's called the resistance to motion. You know, if you're going to push on this thing on the moon, it's going to offer resistance because it's got mass. If you push on it on the Earth, of course, there'll be a different resistance because it's got what we call weight here, because the Earth is pulling on it. So weight changes, mass doesn't. All right. Capacity, certainly you have to have that. If you're going to have any kind of a measuring system, you have to have capacity, volume. Here, can I borrow your? This is 18 fluid ounces. Okay, that's the U.S. customary measurement, right? But now, for some reason, with things like this, bottled water, sodas, and stuff like that, they also put the metric measurement on it. That's been going on for a lot of years. You go down to the Safeway and buy a 2-liter bottle of Pepsi or Coke or something like that. This turns out to be 532 milliliters. So we're going to look at things like liters and milliliters today, and we'll also talk about grams, which is the unit of mass. But the prefix line remains exactly the same. All that changes is this thing right here. Instead of talking about meters now, the unit's going to be grams or liter. This is mass. This is volume. You can also call it capacity. And this, of course, is length. Otherwise, it all stays the same. So if you've got a gram, now a gram is an extremely small amount of mass. Let me see if I have. Yes, I do. Okay. This weighs a gram. Now, that's rather light, right? Not much to it. A penny weighs 2.5 times as much as this. So a gram is extremely small. Okay, but that's what's at the center of the metric system measurement. So, if you're going to talk about a gram here at the center, all right, when you go out here, you're going to have a centigram, which is 1/100th of a gram. 1/100th the mass of the gram. This is a milligram, 1,000th the mass of the gram. You could talk about a kilogram, which would be 1,000 times the mass of the gram. Okay? So bigger this way, smaller this way. But the conversion is exactly the same. You can use the conversion factors if you wish, or you can use the prefix line simply to shift decimals back and forth. So let's take a little look at these things. There's not much difference here. The prefix line with grams in it is there on page 434 in the middle, if you'd like to see it written out. We're going to take 1.6 kilograms, and we're going to say, all right, how many grams is that? Now, we know that this prefix line is a matter of multiplying by 10 or dividing by 10, depending on which way you're going, which means it's a matter of taking your decimal point either to the right or the left. Okay? So we go up here, and we say, I'm going to start at kilograms, right there. And I want to go to grams, which is right here. And it goes boing, boing, boing. We're to the left. So you take the 1.6, here's its decimal point, 3 to the left. 1, 2, 3. And that is 1,600 grams. That's the easy way to do it. That's the way the kids do it in Europe. Okay? Not necessary to use the conversion factors. Let's do a few more. Suppose we do 1,400 milligrams, and we want to know how many grams that is. Okay, now in this case, we're starting with milligrams, which means we're back here. That's the starting place. And to get to the ending place, grams, we go 1, 2, 3 to the right. Oh, to the left. I'm sorry, I'm getting left and right mixed up. Oh, dyslexia. All right, so we start out with this. There's the decimal point for 1,400. It's always just to the far right of the number itself. And in this case, we have to go that way 3 times. So, boing, boing, boing. So this is 1.4 grams. That's it. Very simple. Very intelligent, decimally, it's a decimal-based unit system. And it's very intelligent. Okay, let's look at capacity. The basic unit of capacity is called the liter. Strangely enough, in this one area of selling things like bottled water and sodas and so forth, they have brought the liter into our culture. And that's been, I would say, what, 10 years? Maybe a little more, 15 years, something like that. Before that, if you bought a container of Coke, it would not say liter on it, but now it does. So in other words, there's an effort being made to weave it into the culture. I would say it's happening rather slowly, but that's the way habits are. It's just a habit, that's all it is. So let's talk about a liter. A liter is just, in terms of volume, it's just a little bit more than a quart. So it's fairly similar to our quart, and that's fine. That helps a lot to understand how big it is. You do have, again, a prefix line on page 435 with liters in it and so forth. So this would be called a decaliter. This is a deciliter. This is a centiliter. CL is the abbreviation for that, CL. And the liter is always a capital L, by the way. Why, I don't know, but there it is. And CL is the centiliter. This would be called a milliliter, ML. Now, milliliters are important in things like medicine, doses of medicine, injections, things like that. However, there's one thing that your book points out. For some of you might be in going to nursing. Anyone here? Nursing? Okay.
How come the L has to be a capital?
I don't know.
Okay.
Okay.
thanks.
The milliliter actually can also be called by a different name. It's a cubic centimeter. Okay? Cubic centimeter. That's exactly the same thing. Written as a cc, but it really means cubic centimeter. Now, what does that mean? Well, if you think of it as a milliliter, it means it's 1/1000th of a liter. Now remember, you've got something about the size of a quart, okay, a little bit bigger than a quart. Imagine dividing that up into little tiny boxes where you had 1,000 little tiny ones inside, okay? Each one of those would be a cubic centimeter, okay? It would also be a milliliter. So for those of you who are going into medicine or somehow might interface with people in medicine, you have to know that a cc, which is often on a prescription from a doctor, see so many cc's, is really a milliliter. It's 1,000th of a liter. It's rather small. Okay. So given that, let's take a look at some capacity problems. Again, they're done in exactly the same way. 5.5 liters is how many milliliters? Okay, well, we start off with liters, which means we're here in the center, right there. And we're going to milliliters. Milliliters is way over here. Boing, boing, boing. Again, 3 to the right. So you take 5.5, 1, 2, 3. So it turns out that's 5,500 milliliters. All righty. So here's a trick question. 15 cc's is how many milliliters?
15.
Right on. You don't even have to do any decimal points, huh? Obviously, they're the same thing. So that's it. So let's go to 0.8 centiliters. The question is, how many cc's is that? That's a little tricky because you have to remember that this is milliliters. Okay? So you can use the prefix line. All right, you're starting out at centiliters. That's this thing right here. This is centiliters. And you want to go to milliliters. And that's this thing right over here, milliliters. So it's right next door. You go 1 to the right. So you take 0.8, so 1 to the right, which gives you 8 cc's, or if you wish, 8 milliliters. So you just shift it to the right one. Okay. Well, let's get some feeling for how long these things are and how big these things are. A bottle of canola oil holds 946 milliliters. Okay?
What
And they
page are
want
you on?
this- Pardon?
What page are you on?
I'm on page 436. They want this expressed in liters. So they want to know how many liters is this. All right. Here's milliliters, and you want to go here to liters. So you want to go boing, 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 like that. 3 to the left. 1, 2, 3. So it's 0.946 liters. And you can put the leading 0 on there. As I say, most people will put the leading 0 just to make things clear. Not required, but that's sort of being courteous to the reader kind of thing. Okay, let's do some medical applications here so we can see how it actually works in practice. Now, in order to do medical applications, we're going to have to extend this a bit. And that means we've got to take it down to smaller amounts. Because there's some medicines that you dare not take in a large amount, and I'm serious about that. Initially our medicines were derived from plants, and even the basis of modern medicine is usually substances, chemicals that are found in plants. And there are some things in plants which are very useful medically, and they do duplicate them or copy them into chemical kinds of medicines. But some of them have to be in extremely small dosages. And in those small dosages, they act very positively. The body does something, when it gets to, when that kind of substance is put in, the body reacts and a healing occurs. But you go over that dosage and, the patient dies, and that's the way it is. So they have to be extremely careful with these things. So we're going to take it out more now. Okay, we're going to go out. Now this is 1,000 of a liter. Huh? That's what that one is. This would be a 10,000. There's no name for that. This would be 100,000. No name for that. But this one over here would be a millionth of a liter. It's called a microliter. It's also written this way, MCL. Put a C in between the M and the L. It's a microliter. And sometimes in professional papers, they'll use the Greek letter U, which is a small m in Greek, and write it like that, microliter. Okay. Now, having done that, we can start talking about dosages. As I say, these two are never given a name, but this is a millionth of a liter. In other words, 1 million MCLs equals 1 liter. And that's a very, very small dosage. A doctor orders the antibiotic oxacillin for a child. The dosage is 12.5 milligrams of the drug per kilogram of the child's body mass. This dosage is given 4 times a day. All right, now there's a lot going on here. When you have all this information, it's better just to write it down very briefly with a description so your mind starts getting really clear about what you're given here. So let's do that. Doctor orders the antibiotic oxacillin for a child. The dosage is 12.5 milligrams per kilogram of body mass. Okay? The dosage is given 4 times a day. Okay, so that's known numbers, they tell us. Then they tell us one more thing. They say, all right, how much of the drug should a 24-kilogram child get in 1 dose? Now, needless to say, this is technical stuff, and it's very important because behind the idea of nursing and doctoring and so forth are huge lawsuits. Huge. You know, if you're a nurse and you give the wrong dosage, that could be very expensive. There's a lot of insurance to cover it, but still, this malpractice insurance is extremely expensive. All right, 4 times a day. So, 12.5 milligrams per kilogram. We know this child has a body mass of 24 kilograms. So in order to figure out how much the dosage should be, you're going to have to take the 12.5 multiplied by the 24. Okay, 12.5 times 24. But then it's given 4 times a day. And they're asking, first of all, they want to know how much the child should get in 1 dose. So for 1 dose, that's all you calculate. 12.5 times 24. Let's figure out what that is. Okay, that's 300, and that's going to be in milligrams. 1 dose. Okay, it's given 4 times a day, and they want to know how much does the child get in 10 days. So you have to take that number, 300 milligrams, that's every dose, multiply it by 4 times a day times 10 days, which means it gets multiplied by 400. And when you do that, you find out that's going to be
15,600?
12,000 milligrams. Now that sounds like a huge amount of medicine, right? But let's ask, what is it in terms of grams? Let's convert that to grams.
A teaspoon.
Okay? All right, we're at milligrams, which means we're back here. We want to go to grams, that's 3 to the left. So take this, go 3 to the left, it's 12 grams. 12 grams of medicine over a period of 10 days, so it's a little bit more than a gram a day. So it's not as bad as it sounds. You know, when you say 12,000 or something, you say, "Oh, what are you doing to the kid?" Okay, on 438, you've got an example that says this. Convert 0.85 micrograms, no, this is milligrams, sorry, into micrograms. Okay? Now that means we're going to use the same prefix line, but the extended one with micrograms out here. Okay, so we start at milligrams, which is here. We go 1, 2, 3 to the right. So we take this 0.85, 1, 2, 3, and we find it's 850 micrograms. Millionth of a gram, very small. A doctor gives a heart patient an initial dose of 200 micrograms of nitroglycerin. Now, I mean, nitroglycerin is the stuff that blows stuff up, you know? Really, that's what it is. But you give it in very small amounts, 200 micrograms, and it stops the heart from rapid beating and all this kind of thing. How many milligrams is this? 200 micrograms. How many milligrams? All right, so we're out here. 1, 2, 3 to the left. So you take 200, 1, 2, 3 to the left. It's 0.2 milligrams. Very small amount. Okay, now, you've seen the metric system. Conversions are much easier. But now, because of us, we have to do another section, which converts between the two systems. Yeah, didn't see that coming, huh? All right, because there are certain situations where that's got to happen correctly. Here's the story. Several years ago, we sent robotic lander to Mars. Now, we've been sending landers to Mars for a long time. We put more up there than anybody else. So we send this one up. Everything goes fine. It's in orbit around Mars. And the computer says, okay, now we're going to descend onto the planet and so forth. And it starts descending onto the planet, and the jets don't fire. And bam, right into the surface of Mars. There's $500 million of your dollars. NASA is funded by you. Okay? All right, so what happens? Here's what happens. NASA doesn't make anything. They contract it out to other corporations, right? So someone's got to make a jet engine, someone's got to make the fuel tank to bring the whatever they use, whatever fuel they use, into the jet engine and so forth. They may be two completely different companies. The problem is, if one's here in the United States and another's in Europe, someone had better tell one and the other what units they're using, right? Because we have a U.S. customary system, they have a metric system. And the someone didn't do it. And it didn't show up until they got to that stage of having to land on Mars, because the jets weren't used until that moment. Huh? Now that guy, of course NASA figured out who it was right away, he can't run for dog catcher anymore. You know, he is fired, right? Instantaneously.
What I understand, what I don't understand is, I mean, isn't most manufacturing to the metric system in this country? I mean, we may not use it at the grocery store, but doesn't all the scientific equipment in the United States generally use that system? And that's why I've always wondered.
Yeah, but we're not talking about, shall we say, scientific equipment. We're talking about, you know, nuts and bolts here. And that's still, the mechanical stuff in this country is still done with the U.S. customary system.
Okay.
Yeah, that's what's weird about this. I mean, just a simple little error in units costs us $500 million, you know? And we don't want to do that. I don't want my students doing that kind of thing. Okay? So here we go. All right, the table to convert between is on page 443. So this is conversion between U.S. customary and metric. Page 443. Now, why am I writing that up there? Not because I like to write with this ink, but because we're having a test Friday. Okay. So you need to have these tables, the conversion tables for the U.S. customary, this one, and of course also the prefix line. You need to have them on your cheat sheet, huh? Friday. All right. This one, you pretty much get them all in one place. It's nice. They only do 4. And up here you've got length, weight, or mass, and capacity. And here's what you get. I'll write some of them down. You can read them. They're in your book. 1 inch is equal to 2.54 centimeters. So see, we're going now between U.S. customary and metric. 1 foot. Now notice this one. This is an exact equal sign up here. 1 inch is exactly equal to 2.54 centimeters. But the next one has a wavy equal sign. 1 foot. And then you get these squiggly things. Means it's approximately equal to 0.305 meters. Okay, what does that mean? It means that the actual conversion between the two is an unending decimal. It keeps on going, right? It could be the kind that simply never repeats, but it never ends either. So you've got to chop it off at some point, huh? And they chose to chop it off in the thousandths position there. The 5 is in the thousandths position, okay? Which means the next number is probably less than 5, and you're talking about 10,000th of a meter. Who cares? Yeah, that's just too small to worry about. So this is an approximate one. This one is also approximate. 1 yard is equal to, approximately, equal to 0.914. And that's miles. And 1 mile is approximately equal to 1.61 kilometers. And the rest of them go very similarly. They only have 2 up here and they only have 2 over here. This converts between pounds and kilograms, and this becomes to be ounces and grams and so forth. So that's the table for converting between the 2 systems. Now, nice, it's a table again, but you know, because you're going between the metric system, which is very easy to convert, and the U.S. customary system, it's got to go back to the conversion factors. So now we're back to putting the fractions and canceling the units and things like that. So let's do a few of them, just so we get the feeling for it. So you start out with 15 yards, and you want to know approximately how many meters is that. Okay. Well, you go to the table, and what you find out is that 1 yard is approximately 0.914 meters. So you want to take the 15 yards, create an appropriate conversion factor. Again, you want to cancel out yards, go to meters. So you want yards down here and meters on the top. So these will cancel and leave you with meters. So do your unit analysis to begin with. Just get the right unit in the right place to do the canceling. Okay, then you put it in. All right, what we know is 1 yard is 0.914 meters. 1 yard, 0.914 meters. Okay, again, you can think of that as being over 1, multiply tops, multiply bottoms. So the end result is 15 times 0.914, and that will be in meters. And that is approximately 13.71 meters. So the number of meters is less than the number of yards. Why? Because a meter stick is longer than a yard stick. So it takes less of those meters to go a certain distance than it does yards. All right, let's try some other stuff here. So we'll say 180 grams is, again, approximately equal to how many ounces? And for that, we have to go back to the table to get our conversion factor. We take the 180 grams and put it over 1 if you want, multiply it by the correct conversion factor, grams down here, ounces over here. So we get the nice canceling effect, and you find out that 1 ounce is 28 grams. So now you're going to end up dividing the 28 into the 180, because you multiply tops, multiply bottoms, and that's going to be in ounces. And I get 6.43 actually, when you round it, 6.43, and that will be in ounces. So, no new tricks here, same old stuff actually, back to what we wanted to get away from. That's why they invented the metric systems that we were using. All right, is there anything else worth doing? Oh, yes. Oh, let's look at that. This is actually worth doing. On page 446, you've got the two systems of temperature. Now, is one metric and one U.S. customary? Not exactly. It was not done at the same time as the metric system. What you got here on the, let's see, that would be on your left-hand side. This system is called the Fahrenheit temperature system. It's what we're used to. If you went over to the thermostat in the room, wherever it happens to be, right over there, you find out that the degrees are in Fahrenheit, degrees Fahrenheit. That's the common measurement that we're used to. That's a very old system. No one quite understands why it was created the way it was created. In Fahrenheit, you know, what's the freezing point of water? 32 degrees, right? What's the boiling point? 212. Yeah. 32 and 212? I mean, that's not something anyone would expect, right? Couldn't they have devised a system that works better than that? They did. And it's called Celsius. Now, I think Celsius is actually the name of the man who did it. But this is still 100 or 200 years old, something like that. And it is kind of the metric system for temperature. Because if you look at the freezing point of water, it's not at 32 degrees, it's at 0 degrees. And the boiling point of water is not at 212, it's at 100. So that there's 100 degrees between the freezing and boiling point of water. Oh, that sounds a little bit decimal, doesn't it? Yeah, and it is. Now, in order for that to happen, not only do the two scales have to start with different numbers of degrees, Fahrenheit, 32 degrees, Celsius, 0 degrees, but the size of the degree has to be different. Because when you go up to the boiling point of water on the Fahrenheit, you've got a whole lot more degrees than you have when you go up to the boiling point of water on the centigrade, or the Celsius. So the size of the Celsius degree is bigger than the size of the Fahrenheit degree. Now, all of that means that the conversion between the two has to be done by a more complicated formula than just maybe what we're calling a conversion factor. And those two formulas are on the next page for you. They look like this. Fahrenheit is equal to 9/5 C plus 32. Now, this is, of course, Celsius, and this is Fahrenheit. And this is 9/5. I can draw a better 5 than that. Or if you want to reverse the formula, you can solve it for C, and you get it's 5/9 times F minus 32. So if you start off with a formula in Celsius and you want Fahrenheit, this would be the one to use, because Fahrenheit is equal to that. And you just plug in the number, figure it out, you got it. On the other hand, if you're starting up with Fahrenheit and you want Celsius, you'd use this formula. So it's plug-in stuff. There's nothing complicated here. So let's put in some common, temperatures and see what happens. For example, the normal human body temperature is 98.6. Now, what system is that in?
Fahrenheit.
That's Fahrenheit, exactly. So let's figure out what that is in Celsius. Well, that would be C equals 5/9 times 98.6 minus 32. Okay. So it's just a matter of PEMDAS and calculators and stuff like that. Why PEMDAS? Because you got two operations, right? You've got multiplication, you've got subtraction. So you have to do what's in parentheses first, right? Does this bring back any memories? Yeah, PEMDAS. Okay. So 98.6, and then we're going to subtract 32. So this gives us 66.6. Okay. Now I want to multiply that by 5 and divide by 9. Okay. So I'm multiplying by 5, and then I take that and divide it by 9. And it comes out to be 37 degrees Celsius. So that's the human body temperature in Celsius degrees. If the outside temperature was 98.6, it would feel warm, that's for sure. But that's a high. In other words, you're getting a feeling for a high temperature as far as we're concerned anyway. High temperature in Celsius is up in the 30s. Okay? That's what this is for, to get that feeling. All right, let's do some others that give us some more feeling for this. Convert the temperature inside a refrigerator, which is about 5 degrees Celsius, into degrees Fahrenheit. Okay, so we're starting off with 5 degrees Celsius. Now we want to go to Fahrenheit. This is solved for Fahrenheit, so that's the one we use. So F is equal to 9/5. Now isn't that nice that they chose 5 degrees? Okay, cancel. 9 plus 32 is equal to 41. So inside the refrigerator, 5 degrees Celsius corresponds to about 41 degrees. Now, is that an appropriate temperature for the inside of the refrigerator? Yes, that is. Because if you go too low, if you go below 32 degrees Fahrenheit, you're going to have the water in the vegetables and the meats and so forth freezing, which you don't want to do. Now, you can freeze meat and vegetables, some of them anyway, but you don't want to do that in terms of cooking them for dinner tonight. So 41 is a good temperature, for a refrigerator. Okay, so let's do, we did two sections here, so this is 7.4 and 7.5. And then we're finally through with all this conversion stuff. I used to tell people, look, there's only one purpose for this chapter, and that is insomnia. Can't go to sleep over this chapter. 7.4, here we go.
Must mean the end of class.